Yeah. So happy Thanksgiving. So this week, this lecture will be short, and we will just derive from the. Oh, we finish up with the conformal mapping by now, and before we get into the Fourier analysis, we want to take a rest and go back to study the infinite product and the Weierstrass infinite product theory. So first, let's recall some general facts from Math 521, infinite product. So suppose you have a sequence of complex numbers, then we say this product converges if the limit or the finite truncation exists. And then initial question is, do we have some condition on the convergence of the infinite product? So the answer is we have the following convenient lemma. So if the summation of the absolute value of the sequence an is finite, then the product n from 1 to infinity 1 plus an converges. And moreover, we can show not only convergence, we can show that the limit is bounded below the product so I would like to see in this way. Then moreover, the absolute value of the infinite product has a lower bound that exists absolute greater than 0, such that greater than epsilon and except the case ai equals 0 for certain integer. Also ai equals -1, sorry. Of course, here the epsilon depends on the sequence an. Okay. So to prove it, we just look at proof. It's clear that when n is large enough, we always have the absolute value of an less than 1/2 when n greater than when n is large enough. Then we notice 1 plus so next we do Taylor expansion of 1 plus z for norm of z less than 1/2. This will be z plus z squared divided by 2 and plus z cubed divided by 3 blah blah blah. And then the norm is less than sorry, here you have minus sign. Sorry, my bad. 1 plus z negative 1 plus, yes. And then if you take the norm, it will be less than norm of z plus z over 2 times norm of z plus z squared over 3 times norm of z, blah blah. So it will be less than or equal to norm of z times 1 plus 1/4 plus 1/2, 1/4 plus blah blah. So it will be less than or equal to 2 norm of z. Okay, then let's look at the partial product. This will be exponential log 1 plus an, and so look at its tail. So let's denote this as b, exponential bn. So where bn is summation of bn, and from 1 to capital N, bn is log 1 plus an. Okay, and then look at the product from capital M to capital M prime, where M and M prime are very large. Then this equals product exponential to summation n from capital M to capital M prime bn. And now we noted that when n is large enough, log 1 plus an norm less than 2an, then summation from m to m prime bn, take the absolute value, will be less than or equal to 2 times summation of the partial sum from m to m prime. Okay, then it's clear when m prime goes to infinity, the partial product from m to m prime 1 plus an goes to 1. So this is exactly this means that it's convergent. And then the second part, since the power is convergent, then the limit is exponential summation of bn to infinity. So it's different from zero. Of course, here we need to assume at the very beginning, suppose ai is different from -1 for all I from 1 to infinity. Otherwise, the product is just 0, which holds trivially. Okay, then I will state another lemma, but without proof. The proof is similar. You can either carry out by yourself or look at the textbook. It's in chapter 5, section 3. So suppose now we do a holomorphic version. Suppose fn is a sequence of holomorphic functions on the open set omega. If there exists C1, C2, Cn positive numbers such that the summation of Cn is less than infinity and Fn minus 1 less than Cn for all z in omega, then similarly we have the product converges uniformly in omega to a holomorphic function fz. Secondly, if f and z does not vanish for any n, then f prime z divided by fz is given by the summation fn prime z divided by fn z. Okay, and now we will not prove this here. Now we apply this to some interesting functions. We want to show that. So first, we will show that pi cotangent pi z has a fraction, partial fraction expansion. This will be summation from infinity to infinity 1 over z plus n. So actually you can see this, you have poles at integers, and if you check that, you will find the residue is 1. So the principal part looks like this, and then next we will prove that there's no holomorphic part. Okay, but then the problem is this is not convergent in the usual sense. You cannot change the order. You need to specify in which order you sum them up. Otherwise, you might have 1 over n. How to make sense? Because otherwise you might have 1 over n sequence. This is diverges. Okay, so first step, we will write this as this sum. Think about what we said before, just mention a little bit. If you have, when we talk about the Hilbert transformation, so when you have 1 over z negative epsilon to positive epsilon dz, the integral. So how to 1 to negative 1. How to make sense of it? Because around 0 you have singularities. Okay, then the idea is we truncate it just in a symmetrical way. So 1 to epsilon plus negative epsilon negative 1 over z dz. And then you take a limit. Epsilon goes to 0. Here, same way. This is 1 over z plus m plus 1 over z minus m. You just match them up together. Okay, then we have the following property. We call this as fz. So first, fz plus 1 equals Fz, so it's periodic. Secondly, we already know that Fz has the same, okay, the poles of Fz are 0, positive, -1, positive, -2, all the way up, and the residue and the poles are, and they are simple poles. Moreover, the residue is 1. Therefore, if you consider delta z equals f minus the infinite sum, so understand in this way, then what can we conclude? Then we know that delta z is holomorphic for all z in C, because you cancel out all the poles, and so here the singularities are all of the pole types. And next we want to show that delta is bounded on C. Then you can apply Liouville's theorem. So to prove this, you have two parts. First, we already showed last time, recall that we showed that cotangent for because of the periodicity, we first try to bound Fz at near the infinity. So you consider this, and with this is a square with length of side 2r, outside of r. This is r negative r, size of 2r, and then by the periodicity, you can actually restrict to the stripe near 0, so length 1. Okay, you only need to consider this region. Okay, then when you do estimate, you will, just as what we did last time, you will see it's bounded by the value of pi cotangency inside this fixed small region. This size is 1. Okay, then I will not repeat the proof explicit here. It's in the previous lecture when we talk about the how to compute the summation Pn divided by Qn using residue theorem. Okay. okay, same argument, so we can see pi cotangent pi z is bounded by some constant when z is larger. Of course, here this is a very wiggle way because actually you have poles in the integers. So actually what we want to prove is the delta z is bounded. But this part just bound those sides. Avoiding the poles. Okay, I will not give two rigorous proof here, but then for just give you some idea. Then the next part, look at the series part. And we know that if y is greater than 1, then the norm of this one will be less than some constant times summation y divided by y squared plus n squared. And this will be bounded by constant times y squared plus x squared divided by y divided by this dx. And if you change the variable, it's from 0 to infinity. Change the variable, x is yt. Then you have this integral is the same as 1 over 1 plus x squared. Sorry, t squared. From 0 to infinity dt. So finally this is bounded. Okay, then we are done. We know that delta z is a constant, but notice that delta z is odd. Then delta z must be 0. So we show that pi cotangent pi z equals an infinite summation 1 over z plus 2z over z n minus n squared. Okay, then we noted that let g z equals sine pi z over pi, and pz equals z times the infinite product. So first, we can show this is well defined by the previous lemma on the convergence of infinite product. Okay, now consider derivative of g divided by g, which is just pi cotangent pi z, and the derivative of p divided by p is 1 over z plus the summation 2z divided by z squared minus n squared. Therefore, if you compute the derivative p over g, you will find this is identically 0. Therefore, p over g, therefore p is constant times g. And if you consider g divided by 0 by z and take the limit, or you just consider the residue at 0. this equals the limit p over z when z goes to 0. This is 1, therefore c is 1. So as a conclusion, we show that sine pi z divided by pi is z times the infinite product 1 minus z and z squared minus n squared. Okay, next we want to generalize this type of question arbitrarily. So first, look at what we did. We already know that sine pi or cotangent pi has pi z has zeros or poles along this side, and then we prescribe something here and want to say that's all. So a question is, general question is, given a sequence of complex numbers which goes to infinity, can we find an entire holomorphic entire function, in other words, which is holomorphic on C, f, that vanishes at all an equals or z equals an and nowhere else. So here the multiplicity counted, then if I should state in this way. So we arrange those numbers and such that I probably it's better to see in this way. Suppose point B, suppose number B appears in the sequence m times, then f are required to have to vanish at z equals b to order b. So this is so-called multiplicity counted. Okay, and then the proof, the naive idea is that we just times z minus an together, but of course this blows up because an goes to infinity. If you take z to be 0, this is infinity. Okay, then fix this. How to fix this? Then we might think, oh, let's divide it by an. So let's consider the product 1 minus z to an. They divide by an. But then another question is, still we have question because might be an might go to infinity very slow. so cannot, so 1 over an does not decay very fast, so probably this go to infinity. Then we cannot apply the previous theorem. So, but we have advantage if summation 1 over an less than infinity, so by lemma the function is well defined. So we do have some function. Okay, then to deal with this property, the idea is instead of 1 minus z divided by am itself, we try to time some function which decays very fast. Okay, so here, so probably let's see how to say m and z, so that after modify it, if we write down as some function like this, then we have the norm of f and z, sum them up is less than infinity. Okay, now let's figure out what is mn. So recall that one over z divided by an. Sorry, for this moment, let's consider the model type. So define E0 z equals 1 minus z. So no matter what an you have, you just substitute z by z divided by an, you have the result. And look at what is 1 over 1 minus z. This is exponential log 1 minus z. And if you do Taylor expansion, so you will have z plus minus, this is minus z squared over 2 minus z cubed over 3 minus all the way up. Okay, and so if you want to make this term small, then note that if we can cancel out first a few terms, then this index will be small. Okay, so we make the following lemma. If normal z less than or equal to 1/2, then 1 minus ekz less than or equal to c z2k plus 1's power for some c greater than 0. And here ekz is defined by 1 minus z exponential z plus z norm squared divided by 2 plus all the way up to zk2 divided by k. Okay, so let's prove this. So recall that ekz is log 1 minus z plus z squared divided by 2 plus z to k's power divided by k. Let's denote it by exponential to omega. And then omega z less than or equal to 1/2. Then omega can be written as the infinite sum, n from k plus 1 to infinity, zn divided by n. And since norm of z less than 1/2, So this will be less than or equal to, so norm of omega will be less than or equal to 2 norm of z to k plus 1's power. And then in particular, omega is less than 1. Then 1 minus ekz norm is 1 minus omega, or exponential omega. So less than or equal to some constant times omega norm less than z to k plus 1's power. Okay, now we are done with the lemma. Then you see we have a good control of each factor. So consider holomorphic function defined by z to m's power. So m corresponds to the variation required for the holomorphic function at origin. Infinity en z divided by an. Okay, then we can write it down as infinity 1 minus 1 minus en z divided by an. Okay, then by previous lemma, we know that 1 minus en z over an is bounded by c times z divided by n plus 1's power. Okay, and therefore for fixed z, this we can choose so any fixed term, this is a constant, then choose capital N such integer capital N such that when n greater than capital N, norm of an is greater than 2 norm of z. Therefore 1 over en z divided by an norm less than or equal to c times 1 over 2n plus 1's power. As a conclusion, we show that the summation of this is bounded, and by lemma, we know the product fz is convergent, so this is well defined holomorphic function, and you can easily check satisfies all the properties. Okay, there's another version of the infinite product due to Hadamard, so I don't have time to see this. If you are interested, you can look at the proof therein. It's in chapter 5, section 5.